Rainfall erosivity and soil erodibility. Rainfall and soil. Erosion is affected by rainfall and soil characteristics. If the intensity of rainfall is high, let us say that the intensity is more than 25 millimeters per hour, then it has tremendous ability to erode soil. Some soils are more vulnerable to erosion than other soils. So, impact of rainfall on erosion and soil's vulnerability to erosion are the key factors in erosion rates. Soil erosion is determined mainly by the interplay of rainfall erosivity and soil erodibility. What is rainfall erosivity? It is the force which can detach the soil particles. And soil erodibility is the susceptibility of soil to get eroded. So erosivity acts as a force which can detach particles, and erodibility is the resistance to this force. And the erosion occurs when erosivity surpasses erodibility. When rainfall erosivity is greater than soil erodibility, erosion will occur. Rainfall erosivity. Raindrops possess kinetic energy, aiding in the detachment of soil aggregates and transportation of soil particles by flowing water. The flowing water also possesses kinetic energy, and when the velocity of flowing water is not sufficient, these particles get settled. Surface runoff also accumulates kinetic energy as it traverses the sloping terrain. Higher the slope, higher is the kinetic energy. Raindrops gain 256 times more kinetic energy as they fall on land compared to runoff. So raindrops also possess tremendous amount of kinetic energy. It is 256 times more than runoff. The kinetic energy of raindrops can be computed if the size of the raindrop is known and terminal velocity is known. So if you know the raindrop size and terminal velocity, you can calculate the kinetic energy of raindrops. What is terminal velocity then? It is the constant speed that a freely falling raindrop eventually reaches when resistance of air prevents further acceleration. Now the speed is constant. Now this speed is the terminal velocity. Terminal velocity is the function of size of raindrop, shape of raindrop, density of air, viscosity of air, but we will not get into much details right now. So what is the typical velocity for a small raindrop? It will be somewhere in the range of 2 to 3 meters per second. And for large raindrops, the velocity could be up to 9 meters per second. Terminal velocity, it ranges from 4 to 10 meters per second. Rainfall erosivity. Erosivity is defined as the potential ability of rainfall to cause erosion. Rainfall impact helps seal the soil surface and increase runoff. Now what happens because of the raindrops which fall on the land with kinetic energy? It will seal the soil surface. So some tiny pores get sealed because of the splashing action. And because of the sealing of this soil surface, there will be higher runoff. Soil erosion from a single storm can be estimated using product of storm's total kinetic energy. Let us say rainfall occurred for 1 hour. So what was the total kinetic energy of this rainfall event? And its maximum 30-minute intensity. So product of this will help you in estimating the rainfall erosivity. Rainfall erosivity is a crucial factor in the universal soil loss equation. A is equal to RKLSCP, where R is rainfall erosivity. Now let us learn something more about rainfall erosivity index. Now the best estimator of soil loss is a compound parameter. It's the product of kinetic energy and the 30-minute maximum intensity occurring during the storm. Now it can be calculated mainly by EI30 index method and KE greater than 25 method. EI30 index method. By using this method we can calculate kinetic energy like this. E is equal to 0.119 plus 0.0873 multiplied by log of I. I is the intensity here. Now this equation is valid for intensities which are less than or equal to 76 millimeters per hour. If the intensity is more than 76 millimeter per hour, directly you have to use the value 0.283. This will be the kinetic energy. So on substituting the value of intensity, we can calculate the kinetic energy. Then this kinetic energy is multiplied by 30-minute maximum intensity to get the R value, rainfall erosivity index. Now I30 is the maximum amount of rain which occurred in 30-minute period and which is to be converted into intensity, millimeters per hour. EI30 is R. Okay, it is the product of kinetic energy and intensity I30. KE greater than 25 index method. This is similar to EI30 index method, but in this method only those intensities which are greater than 25 millimeter per hour are considered. Other intensities are not considered because they may not cause a significant amount of erosion. So only those intensities which are greater than 25 millimeters per hour are considered in KE greater than 25 index method. But we'll be using the same equation, 0.119 plus 0.0873 log of I. Okay. Now let us learn the procedure for calculating erosivity index by EI30 method. First, you need to obtain a mass curve. Mass curve is the curve of cumulative rainfall versus time. So obtain the mass curve of the rainfall event from the recording rain gauge. Usually from a self-recording rain gauge, this kind of mass curve can be obtained. So once you get the mass curve, you can prepare a table which will show the rainfall depth at regular time intervals from the mass curve. So you can keep any time interval that you want, but it should be same. Let us say 5 minutes like that. Okay. So at regular time intervals, you can prepare the rainfall depth table. Then you have to compute the rainfall intensity in millimeters per hour or centimeter per hour for each time interval. Okay, so within those 5 minutes, what is the intensity? Okay, so depth is converted into intensity. So in 5 minutes, let's say 10 millimeters of rainfall occurred. So in 60 minutes, that is 1 hour, how much rainfall would have occurred? That is the intensity. We will also do the calculations. Okay, so while doing the calculations, you will understand how we convert the depth into intensity. Now, once you obtain the intensity, you can calculate the energy per unit rainfall depth using the equations provided by Wishmer and Smith mentioned in the previous section. So we have already mentioned those equations. All you need to do is substitute the value of I in those equations. Okay. So if the intensity is less than or equal to 76 millimeter per hour, by substituting the value of I, we can get the kinetic energy. Kinetic energy is then multiplied with the rainfall depth that occurred in the time interval. Okay, so these are the 5 steps. Then the total kinetic energy is then obtained by adding all the calculated energy. Okay, so obtain the total kinetic energy, identify the maximum rainfall depth that occurred in any successive 30 minutes of rainfall event and convert it into intensity. So identify maximum rainfall depth that occurred in any successive 30 minutes, and then that is to be converted into intensity. Finally, the rainfall erosivity index is the product of total kinetic energy and the 30-minute maximum intensity that occurred during that rainfall event. So R is kinetic energy E multiplied by I30, which is the 30-minute maximum intensity. So if unit of kinetic energy is taken as megajoules per hectare and rainfall intensity is taken in millimeters per hour, what will be the unit of rainfall erosivity index? Multiply them. So it will be megajoule millimeter by hectare hours. Okay, so this is the unit of kinetic energy, and I is intensity, millimeters per hour. So R will be megajoules millimeter per hectare hour. Let us understand this procedure by solving this problem. Once we solve this problem, we will understand all the steps. Calculate the rainfall erosivity index R by EI30 method from the given mass curve of rainfall. So the mass curve has already been provided to us. Mass curve is rainfall depth versus time. So let us see. So we have taken a rainfall event of 1 hour. 60 minutes, and this is the cumulative rainfall depth. At the end of 1 hour, what is the rainfall depth? It is 30 millimeters. Okay, and now at regular time intervals, we can see the cumulative rainfall depth. After the first 5 minutes, it is 1 millimeter. After adding another 5 minutes, that is now total 10 minutes, it is 2 millimeters. And if we keep on going like this, at the end of 1 hour it is 30 millimeters. So from this cumulative rainfall depth, you can make this kind of a table. And now let us do the steps. Okay, so now a hyetograph has been made here. This is the hyetograph. Hyetograph is the graph of rainfall intensity versus time. So in the first 5 minutes, what is the rainfall intensity? It is 12 millimeters per hour. See, the amount of rainfall that occurred was just 1 millimeter. That is rainfall depth. So in 5 minutes, 1 millimeter of rainfall depth was recorded. So in 60 minutes, what will be the rainfall depth? So that will be 60 multiplied by 1 divided by 5. So the answer will be 12. So this is the rainfall intensity, 12 millimeters per hour. So in the first 5 minutes, the rainfall intensity is 12 millimeters per hour. In the next 5 minutes, that is between 5 to 10, it is same. Then from 10 to 15 minutes, it is 24 millimeter per hour. So we have calculated intensity for each 5-minute increment of time. Okay, so 0 to 5, 5 to 10, 10 to 15, and so on. Now you need to make this kind of a table. Time interval, cumulative rainfall, rainfall in each 5-minute time interval. You can take any other time interval also. But for our convenience, we are taking 5 minutes of time interval. Then it is to be converted into intensity. We just saw how it is converted. Then once intensity is obtained, you can substitute the values and obtain the energy per unit rainfall. That is to be multiplied by the rainfall to get the total energy. So let us see. So this is the time interval from 0 to 5 minutes, from 5 to 10 minutes, 10 to 15, and so on. Last it is 55 minutes to 1 hour. So time interval is 5 minutes. It's a constant time interval. Okay. So 5 minutes like this. 12 times because rainfall event is of 1 hour. Okay, 60 minutes. So cumulative rainfall, this values have already been provided to us. So total rainfall is 30 millimeters at the end of 60 minutes. Now we are interested in getting the rainfall in each 5 minutes of time interval. So in each 5 minutes it will be 1, next it will be 2 minus 1, so it will be 1, next it will be 4 minus 2, so it will be 2 here. So this is the rainfall in each 5 minutes of time interval. Then 5 minus 4, 1 millimeter, 8 minus 5, 3, 12 minus 8, 4, 18 minus 12, 6, and so on. In 5 minutes, 1 millimeter of rainfall, 1 millimeter of rainfall occurred. So in 60 minutes, it will be 60 multiplied by 1 divided by 5. So that will be 12 millimeters per hour. So intensities have been calculated like this. Okay, 12, 12, 24, 72 you can see because 6 millimeter of rainfall occurred in 5 minutes. Okay, so in 60 minutes it will be 72. So this is how intensities have been calculated. Now we will use the equation, plug in the values of intensity and get the value of energy per unit rainfall. E is in megajoules per hectare millimeter. So for all the intensity values, we can get the corresponding energy values. Okay. So once this is obtained, it is multiplied by rainfall in each 5 minute time interval. So 0.213 multiplied by 1 is 0.213. Here it is 0.239 multiplied by 2. Okay, so it is somewhere in this range, 0.479. Okay, so here it is 0.266 multiplied by 4. So the answer is 1.063. So do this for all the values and get the energy in megajoules per hectare. We need the energy in megajoules per hectare. That's why we have multiplied energy per unit rainfall by the rainfall in each 5 minute time interval. On adding the values, we will get the answer 7.63 megajoules per hectare. This is the total kinetic energy. Okay, 7.63 megajoules per hectare. This is to be multiplied by 30 minutes of maximum intensity that occurred in this rainfall event. Okay, so let us find out the value of maximum 30-minute intensity I30. Identifying maximum 30-minute duration rainfall depth and converting to intensity. So it should be successive 30 minutes, right? So rainfall, let us say it started at this 12 to 12:30 like this. So in the first 30 minutes, the rainfall depth is 12 millimeters. In the next 30 minutes, so which next 30 minutes are available? I have the data at every 5 minutes of interval. So from next 5 to 35 minutes. Okay, so this is 12:05 to 12:35 like this. And the next successive 30 minutes, the rainfall depth is 17. Now keep on increasing 5 minutes. So in the next 10 to 40, this is again 30 minutes of duration. Okay, so we are increasing time by 5 minutes. So 10 to 40, what is the rainfall depth? It is 19. So we have calculated this for all the successive 30 minutes. 0 to 30, 5 to 35, 10 to 40, 15 to 45, 20 to 50, 25 to 55, 30 to 1. And this is the 30-minute duration of rainfall depth. Now you can observe here that the highest depth is 22, which occurred between 12:20 to 12:50. In this 30-minute duration, the rainfall depth was maximum. Okay, it is 22 millimeters. So now it is to be converted into millimeters per hour. So in 30 minutes, Rainfall depth is 22 millimeters. So in 60 minutes, rainfall depth will be 60 multiplied by 22 divided by 30. So answer will be 44. Yes, maximum. Answer will be 44 millimeters per hour. Now we have the value of total kinetic energy, 7.63 megajoules per hectare, and we also have the maximum 30-minute intensity, which is 44 millimeters per hour. Let us multiply them. So R is equal to E multiplied by I30. We will get the final answer. (335.72 megajoules millimeter per hectare hour). This is the value of R, Rainfall Erosivity Index. Now this is another method to calculate the rainfall erosivity index. The value that we will obtain here using this method may be slightly less than EI30. Why? Because we will not consider intensities which are less than 25 millimeters per hour. We will only consider those intensities which are greater than 25 millimeters per hour. So, low intensities of rainfall cause no erosion, or it may cause insignificant erosion, you can say. And there is a threshold value of intensity at which the rain starts to become erosive. So what is that threshold value of intensity? So in this method they have considered 25 to be the threshold value. So experimental evidence has confirmed that rainfall intensities less than 25 millimeter per hour, that is 1 inch per hour, have not resulted in significant erosion. So Ke greater than 25 index method indicates that total kinetic energy of the rain falling at intensities greater than 25 millimeter per hour is considered. Other intensities are not considered. Now let us calculate the rainfall erosivity index using Ke greater than 25 method. Okay. So now we have a rainfall event. Okay, so rainfall started at 9 o'clock, let's say, and between 9 to 9:05 the depth was 0.5. Then at 9:10 the total depth was 1.5 millimeters. At 9:15 it was 3.5 millimeters, and at 10:05 the cumulative rainfall depth is 37 millimeters. This is the mass curve of the rainfall. For our convenience, we will take a regular time interval of 5 minutes. Okay, so we will obtain those depths, we will convert them into intensities, we will use the value of these intensities into the equation and get the value of kinetic energy. So this is the hyetograph. Hyetograph is the graph of rainfall intensity versus time. So on the y-axis we have rainfall intensity, not depth. Okay, and on the x-axis you can see that the time duration is provided 9:00 to 10:05, and these are the intensities. Okay, so it's a similar table, similar to EI30 index method, but here we will not consider intensities less than 25 millimeters per hour. So this is the time interval, 5 minutes we are taking for our convenience. This is the cumulative rainfall, it was already given to us. Now rainfall in each 5-minute interval is this, 0.5, 1. How did we get 1? 1.5 minus 0.5. Okay, 1.5 minus 0.5. Then here the rainfall in depth is 2. This is obtained by deducting 1.5 from 3.5. 3.5 minus 1.5 is 2. Similarly, 6.5 minus 3.5 is 3, and so on. So these are the rainfall depths which are to be converted into intensities. So 0.5 millimeter of rainfall depth occurred in 5 minutes. So what will be the rainfall depth in 60 minutes? Okay, if you ask that question, you will get the answer as 6 millimeters per hour. Okay, so here also maximum intensity is 72. Okay, which occurred between 9:30 to 9:35. Now substitute these intensity values into this equation, energy per unit rainfall. So on substituting, we will get the energy as 0.19 megajoules per hectare millimeter, 0.21 megajoules per hectare millimeter, and so on. Now 0.19 is to be multiplied by 0.05. 0.21 is to be multiplied by 1. Okay, we are multiplying to get the total energy. Okay, we want the unit to be megajoule per hectare. We don't want this millimeter. We are multiplying this energy per unit rainfall by rainfall in each 5-minute time interval. So we are getting these values. So we are following the same procedure as in EI 30. Okay. Now the only difference is now we will reject these values. Why are we rejecting these values? Because here the intensity is 6 millimeter per hour. Okay. Here it is 12 millimeter per hour. Next it is 24. Okay. So we are going to reject these intensities, and therefore these energies will not be taken into consideration. Next, 36 millimeter per hour. Yes, it is greater than 25. We will consider this. So 0.76 is considered here. Similarly, 48 millimeter per hour will also be considered. And we have rejected all these intensities which are less than 25. And then we will take sum of only these intensities that we had accepted. Okay. So total energy is 9.66 megajoules per hectare. Let us identify the maximum 30-minute duration of rainfall depth, and then we will convert it into intensity. So maximum 30-minute rainfall depth is 30 between 9:15 to 9:45. Okay. Between 9:15 to 9:45, it is 30 millimeters. So in 30 minutes, 30 millimeter is the maximum rainfall depth. So in 60 minutes, it will be how much? It will be 60 multiplied by 30 divided by 30. So it will be 60. Okay, double of this. So we have the value of energy, which is 9.66 megajoules per hectare, and we also have the maximum intensity, 30-minute intensity, which is 60 millimeter per hour. On multiplying them, we will get the rainfall erosivity index. Okay, so rainfall erosivity index is 579.6 megajoule millimeter per hectare hour by KE greater than 25 method. Now let us learn about soil erodibility. Soil erodibility is defined as the susceptibility or vulnerability of soil to get eroded. Some soils can get easily eroded. Let us say soil is dry, it is in loose condition. So this kind of soil can get easily eroded. And some soils which are having good moisture, they are having finer particles, but they are behaving as a cohesive unit. Okay, there's a lot of cohesion force between them. Then it will be difficult to detach those soils. Okay. So the physical characteristics of soil and land management practices affect soil erodibility. It is possible to evaluate the physical properties of soil more effectively compared to management practices. Characteristics of soil which we can evaluate are texture, aggregate stability, shear strength, organic matter content, and infiltration capacity. All these characteristics affects the soil erodibility. Now let us learn how to obtain soil erodibility. Now we can calculate soil erodibility by constructing this kind of a runoff plot. Now this is a runoff plot having length of 22.1 meters and it is having a constant slope of 9%. So soil erodibility can be estimated based on the soil loss that occurs in the unit plot of length 22.1 meters and 9% uniform slope. So let us say it is sloping in this direction. So all we need to do is collect the soil. Okay, collect the soil here. So soil loss that occurs from this unit plot gives an indication of soil erodibility. Erodibility factor K appearing in the universal soil loss equation is the rate of soil loss per unit of rainfall erosivity R for a specified soil. See, universal soil loss equation is A equal to R K L S C P. Okay. So if the values of K, L, S, C and P are 1, then A will be equal to R multiplied by K. Okay. Then K will be equal to A divided by R. So based on that, they have written this sentence that erodibility factor K appearing in this universal soil loss equation is rate of soil loss A divided by R. So rate of soil loss per unit of rainfall erosivity R for a specific soil. Okay. So K is equal to A by RLSCP. If the values of LSC and P is 1, then K will be A by R. For a unit plot, interestingly, the value of topographic factor, that is LS, will be equal to 1 and values of C and P will also be equal to 1. So here is a barren plot, okay, of 9% slope and length 22.1 meters. This is the runoff plot which can be used to estimate the soil erodibility. Now soil erodibility can also be estimated using a series of equations. Now K is equal to K1 plus Ks plus Kp, where K1 is the first approximation of K. Ks is the soil structure subfactor and Kp is the permeability subfactor. K is the summation of all this. K1 first approximation, Ks soil structure, Kp permeability. Now Ks can be approximated by using this equation. Ks is equal to 3.25 multiplied by 10 raised to minus 2 multiplied by B minus 2. Here B is the code assigned to the soil structure. Okay, so B is the soil structure code. Kp appearing in this equation can be estimated using this. Kp is equal to permeability subfactor is equal to 2.5 multiplied by 10 raised to minus 2 multiplied by C minus 3. C is the code which is assigned to soil permeability. C is the code assigned to soil permeability. Next, now K1 is equal to Kt multiplied by K0. K1 is the first approximation of K, right? Now Kt is equal to 2.1 multiplied by 10 raised to minus 5 multiplied by m raised to 1.14, and K0 is 12 minus A multiplied by 10 raised to minus 1. Here Kt is the soil texture subfactor. K0 or Ko is the organic matter subfactor. M is the particle size parameter, and A is the organic matter content. Okay, so here you can see that if you get the values of Kt and K0, you can get the first approximation of soil erodibility, K1. So M, which is the particle size parameter, is the percentage of 0.002 to 0.10 millimeter multiplied by percentage of 0.002 to 2.0 millimeter size. Okay, so this will give you the value of M. These equations will initially seem a little complex, but once we solve one example, you will become familiar with these equations. So right now you need to remember what is K1, Ks, Kp, Kt, K0, M and A. Okay. So in the original formulation, both the equation and the nomograph written K factor values in the term of customary US units. So it will return in US units, 0.01 ton acre hour by acre feet ton inch. Okay, so but here we are more familiar with our conventional units, international metric system. Okay, so if you want to convert this to ton hectare hour by megajoule hectare millimeter, you need to multiply the value by 0.1317. So once you obtain the answer here, just multiply it by 0.1317 to get the answer in international metric system. So let us estimate the soil erodibility for the soil. Once you solve this example, you will become familiar with the equations. Now, upon analyzing the soil, it was found that the soil particle size between 0.02 to 0.10 millimeter was 60. Okay. Then between 0.10 to 2.0 millimeter it was 7. Okay, so total it will be 67 between 0.002 to 2 millimeter. We'll be using these values. Organic matter is 0.6%. Structure index is 4 and permeability class is 4. From this, let us try and estimate the soil erodibility using those equations. So now M is the percentage of size ranging from 0.002 to 0.10 millimeter multiplied by percentage of 0.002 to 2 millimeter. So here we'll be multiplying 60 and 67. So M is equal to 60 multiplied by 67, which is 4020. Now next we will calculate Kt, the texture subfactor. It is 2.1 multiplied by 10 raised to minus 5 multiplied by m raised to 1.14. So on substituting the value of m, you will get the soil texture subfactor Kt as 0.27. Now Ko is 12 minus A multiplied by 10 raised to minus 1. So A is already given to us. It is 0.6%. Organic matter percentage is 0.6. So A is 0.6. On substituting the value of A, we will get the value of K0 or Ko, let us say. Ko is 1.14. The structure subfactor 3.25 multiplied by 10 raised to minus 2 multiplied by B minus 2. Now on substituting the value of B is also given to us. B is 4. So on substituting the values, we will get the answer as 0.065. Now Kp is 2.5 multiplied by 10 raised to minus 2 multiplied by C minus 3. C is the permeability class. On substituting value of C, which is again 4, we will get Kp equal to 0.025. So we have obtained the value of Kt, K0, Ks and Kp. So M, Kt, Ko or K0, Ks, Kp. So K1 is equal to Kt multiplied by Ko. Now, do we have the value of Kt? Yes, it is 0.27. So, on multiplying them, we get the value of K1 as 0.31. Now, K is K1 plus Ks plus Kp. So, 0.31 plus 0.065 plus 0.025 will be equal to 0.40. This is the value of K. K is 0.40 multiplied by 0.1327. Okay, so on multiplying them, you will get the final value of K as 0.05 ton hectare hour per hectare megajoule millimeters. This is the value of soil erodibility. Now, let us use the same values and estimate soil erodibility using a nomograph. Now, percentage silt plus very fine sand is 60. Okay, so let us start with 60 here and make a horizontal line. It will touch the percentage sand line, which is 7. Okay, it is touching sand percentage line. Now we have to go vertical. Percentage of organic matter is 0.6. So up to 0.6 will go vertically, and then again horizontal will go. The soil structure is 4, so we'll touch the line to soil structure 4 line. Okay, so horizontally we have gone and drawn this line up to soil structure 4 line. Then soil permeability is 4 again, so we'll go vertically downwards now up to soil permeability 4 line, and then finally again horizontal on the left side here, so it will touch somewhere near 0.05. Okay, so this is the soil erodibility, 0.05. Now we have calculated this using a nomograph. You can either use the equations or you can use the nomograph. Estimate the soil erodibility for this soil. Let us now, size between 0.002 to 0.10 millimeter is 51. So this is the percentage size which is given to us. Size between 0.10 to 2. In this range, the size is 7%. Then from 0.002 to 2 millimeter, it is 58%. 51 plus 7. Organic matter percentage is also given to us. It is 0.4%. Structure index is also given to us. It is 4. Permeability class is also 4. So it is similar to M will be equal to size ranging from 0.002 to 0.10, which was 51, multiplied by percentage of 0.002 to 2, which is 58. So 51 multiplied by 58 will give you 2958. Then KT is 2.1 multiplied by 10 raised to minus 5 multiplied by M raised to 1.14. On substituting, we will get the value of KT also. It is 0.19. KO is 12 minus A multiplied by 10 raised to minus 1. A is 4. A is 0.4 in fact. Organic matter percentage. KS is 3.25 multiplied by 10 raised to minus 2 multiplied by B minus 2. Let us substitute the value of structure index. B equal to 4. We'll get Ks as 0.065, similar to the previous one. Kp is 2.5 into 10 raised to minus 2 multiplied by C minus 3. On substituting value of permeability class, we will again get Kp value as 0.025. So now K1 is Kt multiplied by K0. So Kt is 0.19 here and Ko is 1.16. So we'll get the first approximation as 0.22. Now K is K1 plus Ks plus Kp. Therefore K will be equal to 0.22 plus 0.065 plus 0.025. So answer is 0.31, which will be multiplied by 0.1327 to convert it into international metrics Okay, so we'll get 0.04 ton hectare hour per hectare megajoule millimeter. So this is our final estimation of soil erodibility for this soil. Now let us use the same values and estimate the erodibility using this nomograph. Now percentage silt plus very fine sand in this case is 51%. Okay, so we will go horizontally up to sand percentage 7, then we will go vertically. Organic matter is 0.4, so we'll make a small vertically upwards line. Then again we'll go horizontally towards the right and join soil structure 4 line. Then soil permeability is 4, so vertically downwards will go. So alternately we are going horizontal and vertical. Okay, and then on joining the y-axis of